Today we will discuss about how to solve Rosenbrock banana function using differential evolutionary optimization algorithm. Okay, let us see how we can implement in R language. So before discussing, first of all we should understand what is the fitness value or what is the function for Rosenbrock banana function. So you can type in Google, you will get this function. So this is the function we are going to implement in our program. F of x comma y is equal to a minus x whole square plus b into y minus x square whole square. This is the fitness function we are going to implement and solve using differential evolutionary algorithm. So here the default values for a and b are taken in for our program. So a is 1 and b is equal to 100. So that means the fitness function is 1 minus x whole square plus b 100 into y minus x square whole square. So this is the function we are going to take. Let us see what we are going to do. So here this function is dependent on two variables, x and y. Okay, so the dimensionality is 2, d is equal to 2. Let us see the implementation. So first of all we have to see what is the syntax for this. So the syntax for DE is the syntax. The name of the function for implementing the differential evolutionary optimization technique is DE optim. This is the name of the function. Okay, this is the name of the function. For this function we have to pass the evaluation function or fitness function, in this case Rosenbrock, and then you have to pass the lower range vector, and next argument is higher range vector, and finally a control list you have to pass. So total 1, 2, 3, 4 arguments you have to pass. So let us implement the Rosenbrock and then the control list parameters. So it is a list. Let us see one by one. So for using the differential evolutionary optimization algorithm, we have to load the DE optimum package. Okay, so if you don't find this library, please install it. You can see my right hand side. So there is a button, you can click install and you can type your required package and click the button install. Okay, so automatically the package will be installed. In this case I already installed. So first of all load the library, DE optim library for executing the differential evolutionary algorithm. And the next thing is implement the Rosenbrock function. So I already told you the function here I have taken is a value is 1 and b is equal to 100. That means 1 minus x whole square plus 100 into y minus x square whole square. This is the function we are implementing in R. So after implementing, you can see our function. It is a function on two variables x and y. So therefore this function is dependent on two variables. Therefore the dimensionality is 2. So we initialize d is equal to 2. Okay, and then we will run the algorithm for 100 iterations, and then we will define the control list parameters. Okay, let us see the control list parameters is initialized with the help of this function. It comes with this library, DE optim library, DE optim dot control. With the help of this function, you have to set the parameters of the differential evolutionary algorithm. First one is strategy. What type of strategy you are going to use? Generally, two strategies are there. Okay, you can pass 1 or 2 by default. Second strategy is adopted, and next argument is NP. NP is population size. I already told you this differential evolutionary algorithms, they are also belonging to population based search algorithms. So for each genetic algorithm or differential algorithm or a particle swarm, you need to specify the population size. In this case, 5 population size, and then the maximum number of iterations. So all these you have to define in the control list, and then you have to define the crossover probability. CR means crossover probability. You can see the default is 0.5. So if you want to change the crossover probability, means you have to put the value in between 0 to 1, crossover probability. So before executing this algorithm, I request the students to study about the theory part of differential algorithm. Then only you will understand why we have to set this crossover probability. So maximum number of, these are all control parameters. You have to set the population size, maximum number of iterations, and crossover probability, and F. This is a scaling factor. Generally the scaling factor is in between 0 to 1. Okay, by default 0.8 is there. Okay, you can set this parameter in the control list, and then trace is equal to 25, from where we want to store the population, because during the initial iterations the population will be very much what you say, you can ignore those populations because you will have large fitness values. Actually this algorithm we are going to use, this is also a minimization problem. Okay, so it will give you the minimized optimum solution, from where we have to store the population, and what is the frequency to store the population. You can set these parameters in the control list. Once it is set, you can pass this function to the DE-optim algorithm. So first one is Rosenbrock, so I already implemented for you, and then the lower range and upper range vector and control C list parameters. Here this we have declared using this one. So here in the control list we have to set the parameters, what is the strategy, what is the population size, how many iterations, what is the crossover probability, and the F is scaling factor, all these things. So once you pass all these things, you can execute this algorithm, differential evolutionary algorithm, and it will give you the output, a D object. So you need to understand that D object, okay, D object, it will contains components like optim and member. You have to understand this optimum is again a list only, member is also a list. Again this optimum is a list containing elements best solution and its best value. Okay, so let us after getting the output object, we will extract the best solution and best evaluation value. So let us show the results by using summary command, and we are using this command to fit the output window. So since we are plotting the results, sometimes it will not fit in the right side panel. So for that reason only we use this command, and after that we are plotting the output object. After plotting the output object, plot of D output object. Next thing is you have to print the optimum solution. I already told you output object, you are having the output optim, it is also a list. With this list again you will access the best solution, this is the best solution and its best value. So let us execute statement by statement, you will understand. It is executed. Here the dimension is 2, so I am clicking the run button. So you can see the summary of results. Actually you can see this. So here when you put the trace is equal to 25, so after 25 iterations you are storing the results. What is the best value and what is the best solution? What is the best evaluation value and its solution? You need to remember that we are this algorithm, this DE optim, it finds out minimum value. Okay. So after that, after summary is over, let us plot. Oh, now you can see this. So the topmost curve is about the first parameter x and another parameter is y. Okay, two parameters are there. So for each parameter, how the value changes. Okay, that is a logic here. How the parameter, how the value changes. So you can plot this. Okay. After that, you want to print the best value. So this is the optimum solution and its corresponding evaluated value. This is the minimum value you got, 5.77, and its corresponding optimum solution is minus 1.4, 1.9. In this way, you can execute the program. You can utilize this library. By using this library and by writing our own function and setting our own control list parameters, we can execute, we can solve the problem using differential evolutionary algorithm. Okay. So finally you can print. Thank you, students.